Hello everyone, I'm Fabio Palomba, Assistant Professor at the University of Salerno and specifically at the Software Engineering Research Lab of the University of Salerno. And today I'm going to discuss about mutation testing and specifically how software analytics, mining software repositories and machine learning can help mutation testing and can address a key limitation of mutation testing that we are going to discuss in the next few minutes. Before starting, let me thank the MSR 2020 educational track co-chairs, Abraham Hindol and Alexander Serebrenik for the invitation, for giving me the opportunity to perform to do this tutorial. Okay, that being said, let's start. What we are going to do in the next 30 minutes or so is to understand a little bit more the problem of mutation testing and what are the peculiarities that make mutation testing interesting for mining software repositories and machine learning. In the second place, we are going to discuss how software analytics can play a role in mutation testing. And finally, we are going to see how to implement a machine learning pipeline able to support mutation testing and specifically predict the mutation score of test suites. In so doing, we are also going to discuss and understand some key issues in, let's say, in the pipeline of the machine learning model, and I will provide you with some insights on the key issues and how to address them in the context of a generic problem of machine learning. It is important for me to recognize that this tutorial is based on the paper that you see now on the slide, which is a TSC paper that we recently published. And the tutorial exists also and especially because of Giovanni Grano, who is the first author of the TSC paper, and therefore let me thank Giovanni for the hard work he has done on the TSC paper and for giving me the possibility to use some of the product developed in the context of this paper. Okay. Let's start with the point one of my presentation, which is mutation testing. As you probably know, as most of you probably know, test cases form the first line of defense against the introduction of software faults. And this is especially true when testing for regressions. Indeed, in a typical use case scenario, developers produce new software, keep changing the product, and afterwards they commit these new changes onto a shared repository, right? And in this case, in a typical use case scenario, a number of test cases are automatically run against the newly committed source code in order to identify defects, namely in order to verifying whether the newly introducing changes are defective or not. And it's interesting to know that the outcome of test cases are important for developers for a number of reasons. Indeed, it has been shown in the recent past that developers use the outcome of tests to decide on whether to merge a pull request or not, whether to deploy the system or not. And it has also been shown that the developer's productivity is partially dependent on tests. So this is just to say that test cases are important and represent a key component of every software systems. However, this scenario I just presented makes sense if and only if the test suite is reliable. Otherwise, developers cannot have enough information on the product, on the effectiveness of the software. And therefore, it is crucial for them to measure the quality of a test suite. Now, you probably are aware of the concept of code coverage, which is the key measure, the key metric for measuring the quality of a test suite. Code coverage simply measures the amount of lines of code which are exercised by a certain test case. Despite being extremely popular, indeed many software systems, the vast majority of software systems use code coverage within their, for instance, continuous integration pipelines. Despite being so popular, code coverage is a key issue. Namely, it is a metric that counts, that considers only if a line of code has been touched by a test case, but it cannot give insights on whether the behavior of the system has been exercised. Therefore, because of this reason, the research community has been working on alternative metrics for capturing the quality, the effectiveness of test code. And the key alternative to code coverage is certainly represented by mutation coverage. Mutation coverage measures how many artificially created defects are detected by a test case. What does it mean? Suppose that you have this piece of code, and suppose that you have this line int a equals b minus d. With mutation testing, what you do is to variate the source code in order to produce what we call mutant, namely an artificial version of the original source code that changes, that is supposed at least to change the behavior of the production code. And there exists a number of artificial operators that change the source code. For instance, we have just seen the changing of the operator in an operation. There is the negate condition. There is the change of the return statement of a method. So all these changes have the goal of altering the behavior of the production code. And the idea is to measure how many of these mutants, how many of these artificially created defects are identified by a test case. And so mutation coverage is given by the ratio of the detected mutants over the total amount of mutants generated. Of course, the idea, the conjecture behind mutation coverage is that if a test is able to identify mutants, artificially created defects, it is also able to identify real faults when they present themselves, when they manifest themselves. This is, of course, a more powerful alternative to code coverage. It's clear, but it is also true that mutation testing, mutation coverage is still a non-practical solution. Why? Simply because mutation testing suffers from scalability issues. If you reason about that, applying mutation coverage, mutation testing in practice means that you have to generate mutants. So this is the first step of the process. You have to recompile the source code in order to make the source code testable by test cases. And finally, you have to execute test cases. This process has a cost. And especially in software systems having thousands of tests, this is clearly not feasible. For this reason, researchers in the past have been working on making mutation testing more practical. So they worked on the scalability perspective of mutation testing. And they came up with a number of useful alternatives that we can categorize in three main types of approaches. The first one is related to the do fewer approaches. And these are techniques that aim at selecting a subset of mutants to evaluate. So they work on the first step of the process, the mutants generation step. The second category is the do smarter. What does it mean? It means that techniques in this category aim at exploiting runtime information to avoid unnecessary test executions. So they work on the third step of the process, the test case execution part. And finally, we have the do faster, which are techniques that aim at reducing the overall execution time of single mutants. So they still work on test case execution, on the test case execution part. Do they work? Do these approaches work? Well, yes, to some extent. What does it mean? It means that most of them provide some gain in terms of scalability, but this is not enough. So we need something more. And what we did in the recent past is to exploit mining software repositories and machine learning, so software analytics, in order to make or try to make mutation testing more feasible in practice. And particularly, our idea was to exploit software analytics to learn features that can describe the effectiveness of tests without the need of running them. What does it mean? It means that we conjecture that a number of statically computable metrics, like metrics related to test code quality, test code design quality, can be used within a machine learning approach in order to predict the mutation coverage. So in this case, the prediction would allow developers not to run test cases, or at least to run more expensive mutation testing analysis only for those tests that are predicted as not effective. So let's take a look at how we implemented this solution, how we allow mutation testing and software analytics to meet. And before continuing, I would like to clarify that what we are going to see in the next minutes is something that is just targeted on mutation testing, but most of the steps that we are going to see are generic and general enough to be applied to any machine learning problem. So this is something useful for a variety of problems, not only for mutation testing. The first step, or at least, let's come back for a second. Step 0 of implementing a machine learning model or using software analytics is to understand whether and why a certain problem is suitable for software analytics. Unfortunately, I've seen in the recent past a number of papers which adopted machine learning just for the sake of using machine learning. But this is clearly not enough. To use a machine learning model, to exploit mining software repositories, techniques combined with machine learning models, there must be a clear reason, a clear objective that can be reached by using those techniques. So this is step 0. And in our case, this step 0 was the understanding of whether machine learning could be used to predict the mutation score of tests. Step 1, instead, is to select the dependent variable. What does it mean? It means that you want to identify what is the variable that must be predicted, so the variable of interest. We are talking of mutation testing, so in our case, this was the mutation score. Mutation score, namely, so mutation score and mutation coverage, they are synonyms. Just to recall, it is the ratio between the number of mutants identified by a test over the total amount of mutants generated. To generate mutants, we adopted PIT, PyTest, which is the state-of-the-art tool for mutation testing. And this tool implements 13 different types of mutation operators. So through PIT, PyTest, we were able to generate a number of mutants, so to mutate the production code of a number of systems. It is important to note, and this is one of the recommendations to take into account when developing a machine learning model, is that the dependent variable must be precise, must be valid, must represent an oracle for the machine learning model. Unfortunately, for some problems in the mining software repository field, this is not possible. This is not always possible, at least. For instance, consider the problem of defect prediction, in which you want to understand whether a component was buggy in the past. In this case, you cannot be 100% sure, at least in some cases, and therefore you may need to approximate the dependent variable. And this, of course, creates some bias. And you may want to estimate the bias caused by the approximation. In the second step, when after selecting, let's say, the variable of interest, you want to model the problem. And the problem is generally modeled as a classification problem or as a regression problem. What does it mean? It means that based on the dependent variable, you have to understand what you want to predict in practice. If you want to predict a continuous variable, which is in this case the mutation score, the pure mutation score, which is between 0 and 1, or whether you want to predict a discrete variable. That means that you discretize the continuous values in order to model the problem as a classification. So to classify whether a test is effective or not in our case. In our particular case, we decided to model the problem as a discrete variable. This because you have to know that predicting the exact number, the exact mutation score is something that is, of course, much more complicated and much more fine-grained with respect to model the problem as a classification problem. And of course, what we thought at the time was that developers may want something which is a little bit higher grade, because in this way they could use the classification model as a way to discriminate on which tests some mutation, more complicated and more fine-grained mutation testing analysis should be done. So our idea was to develop a recommendation system that is intended to be support other mutation testing tools rather than replacing them completely. Once decided the dependent variable, you have to dive into this black box, which is the machine learning model. And particularly, it is crucial to conduct a systematic feature engineering process. What does it mean? It means that you may want to select and identify suitable features that characterize the dependent variable. So in our case, what we did was starting by reasoning on which were the features that could characterize the effectiveness of test cases. And we came up with a list of 67 statically computable production and test code metrics. In our case, as also briefly mentioned before, the goal was to create a machine learning model that able to statically decide on the effectiveness of tests, especially because we wanted to address the scalability issue of mutation testing. So that's why we focused on statically computable production and test code metrics. Among them, we identified some metrics like the complexity of source code, test code design metrics, like for instance test melts, which are symptoms of the presence of poor design choices applied when developing test code, and so on. So, but the most important thing here is to understand that we focused on statically computable production and test code metrics. Here, it is important to know, and this is a general recommendation, is that feature engineering is the key to develop an accurate machine learner. Because if you are not able to identify the set of metrics that characterize the dependent variable, you are going to fail. You are not going to develop an accurate machine learner. Let's say the last step to develop a machine learning model is to select a suitable classifier for the problem of interest. What does it mean? It means that you have to identify which of the machine learning algorithms that are available can better fit the problem. In most cases, you don't have any idea of what is the most suitable machine learning algorithm, and therefore you may want to test more than one classifier and see which of them work better for the problem of interest. And this is exactly what we have done with this work. We have tested a number of different machine learners. In particular, we tested three of them. Here are some recommendations. The first one is to configure the hyperparameters of these machine learners. What does it mean? It means that certain classifiers have a number of parameters that may strongly influence the resulting performance. That means that you may want to configure, to tune the hyperparameters in order to create the best algorithm to deal with the problem. The second step, the second thing to know here is that machine learning algorithms differ from each other because of many reasons, because of the reasoning, the assumptions they do on the underlying data, because of the algorithm itself that they implement, and others. And unfortunately, not all features would be always useful for all classifiers. What does it mean? It means that you may want to feed the machine learning algorithm only with relevant information. And this relevant information is given by the selected metrics. But not all the selected metrics may be useful for the classifier. That means that you may want to run some feature selection algorithm, namely the algorithms able to identify which features are the most important features for the classifier. And this is especially important because you may have correlated variables among the set of features that you selected. And correlated variables represent a huge problem for machine learning because the classifier, the machine learning algorithm, cannot properly assign a meaning to the features if the features are correlated. And therefore, the decisions made by the classifier may be biased because of correlated features. So the idea is to discard correlated features. Once applied this preprocessing or these steps, you have a black box, a white box, which is ready to be exercised, to be tested. And this is the second, let's say, big step of supervised machine learning approaches. And here, to evaluate the resulting model, the first thing to do is to collect enough data. Because we are talking of supervised machine learning approaches, which are approaches that need to be fed with enough data in order to learn something. And the training step is generally done with mining software repositories algorithms, depending on the specific problem that you have, of course. What you have at the end of the data collection is something like what you see in the slide. Namely, you have a number of classes, in our case, a number of test classes, with information about the features characterizing those classes. In our case, the 67 features we selected. And finally, the classification of that class, whether this class can be considered effective or not effective. I missed to say that we classified effective and not effective tests by looking at the mutation score. If this was higher than a certain threshold, then it was classified, it was considered as an effective test. Otherwise, it was considered as a not effective test. Here, the important thing to say is that to effectively train a machine learning model, you need enough data for each value of the dependent variable. What does it mean? It means that if you have, like in our case, two classes, effective and not effective tests, you may want to have the same or similar amount of observations for the two classes. Why? Simply because supervised machine learning is about learning, is about training a classifier. And if a classifier doesn't have enough information about some of the classes of the problem, it cannot learn. It's clear. So in some cases, this is not possible because always keeping as example the defect prediction model. In defect prediction, you have that the number of defective classes is generally much lower than the number of not defective classes. This means that you may want to balance the ratio between defective and not defective classes by applying data balancing approaches. There are a number of data balancing approaches like undersampling, oversampling. I'm not going into details, but the idea is to balance the train set. In our case, we were lucky enough because we simply by design of the problem, we had the same amount of effective and not effective tests. So we didn't apply any data balancing approaches for this reason. Then, once you collected data and once trained your model, you may want to know how good is this model. And of course, to evaluate the model, you need something to verify the performance of the model. And what you do in general is to split the collected data into sets, the training and the test sets. Particularly, a particularly famous and exploited technique is called 10 cross-fold validation. What does it mean? It means that you split the original data set in 10 parts. 9 of them are considered for training the machine learning model. One of them is instead retained as a test set. And what you do is to see whether the model trained on the 9 parts of the dataset is able to correctly predict the labels in the test set. And this process is usually repeated 10 times in order to allow each part of the dataset to represent the test set exactly once. In some cases, you may want to configure the parameters while validating the model. What does it mean? It means that if you train a classifier, you may want also to configure the classifier in order to have better performance. What we did, and what is, I would say, a good practice to do, is to have this validation, so training and test set, as an outer validation, complemented with an inner validation, especially specifically used for hyperparameter tuning. What does it mean? It means that on the 9 parts of the original data set that were retained as training set, we used those 9 folds, 9 parts, in another validation process in which we split the 9 folds in 8 and 1. What does it mean? It means that you have 8 folds that are used to train the classifier, and one of them is used to validate the configurations, the different configurations that you apply on the training set. In this way, what you have is that you configure the machine learner on the data available in the training set. And once you concluded this step, you come back to the original validation, to the outer validation, and you apply the configured machine learner on the test set. And finally, what you do is to measure the performance of the machine learner. And usually there are a number of metrics, but usually what you do is to measure precision, recall, and depth measure. Precision computes the number of true positive, so correct classifications, over the total amount of predictions done by the machine learner. In this way, you see what is the ratio between correct and incorrect predictions. Recall instead computes the number of correct predictions over the number of, let's say, instances in the dataset, which are labeled as a specific class. What does it mean? It means that in our case, recall computes the number of effective tests over the total number of effective tests in the dataset. So it's a ratio between the predicted correct instances over the total amount of correct instances. And finally, F measure is just the harmonic mean between precision and recall, and it's useful to have a quick, immediate idea of the performance of your model. So that's it. Time is running out, unfortunately. We have just 10 minutes left, but let me say something more about machine learning, software, managed software repositories, and mutation testing. First of all, I will share these slides, the ones that you see now projected, but also a more complete slide deck, which presents more tips, tricks, secrets on how to use machine learning and how to exploit mining software repositories in combination with machine learning. This additional slide deck is available at the link that you see on the slide. And this is a slide deck that I prepared for my software dependability course at the University of Salerno. So that's why you will see software dependability, the title software dependability in it. I don't have enough time to run the source code that we are going to see in the next few minutes. As you probably know, mining software repositories and machine learning can be super expensive. And if you want to mine things, it's incredibly costly. However, Giovanni and I prepared a Docker machine, which can be used in order to replicate entirely the paper that we discussed in this tutorial. And there is this GitHub repository in which you can find all the instructions, as we are going to see in the next few minutes. Of course, if you have any question about how to run a mining software repository study, how to combine mining software repository with machine learning, how to replicate this study, just drop me an email. This is my email, and I will answer your questions. Now, that being said, let's have a look at how to practically implement a machine learner, and a machine learner for mutation testing in our case. This implementation is based on the Python library sklearn, which is an extremely powerful library for running these kinds of studies, as we are going to see. So let me quickly go. This is the repository I was talking about. As you will see, there are a number of scripts here in this repository which allow you to replicate entirely the paper, the study. And particularly, we provided information about the Docker machine, how to install and run the Docker machine, which are the requirements for the Docker machine, as well as how to replicate this study step by step. And also, we also provided the output of the various experiments we conducted in the paper. As part of the replication package, what you will find is this project, Lightweight Effectiveness. This project contains all data scripts that we used for the study. Let's just have a quick look on that. What you will have here, what you will see here, is that the project contains a number of packages: classification, metrics, mutation. The metrics folder, the metrics package, contains the data required to extract, to mine software repositories in order to extract the metrics which represent the features of the machine learner, as well as how to aggregate different sources. So, for instance, how to aggregate data coming from the historical analysis rather than the analysis of source code. The mutation package contains instead all the scripts required to compute the dependent variable, and particularly how to run PyTest in order to compute the mutation score. And finally, you have the classification part, which is the most interesting part, if we could say. Particularly, it's worth discussing about the classifier.py class. As said, this class uses the sklearn Python library, which is extremely powerful, as I was saying, because in a very few lines of code, it allows you to do whatever you want on with respect to the machine learning pipeline. Particularly interesting is the classification method, which is the method that actually implements the pipeline that we were discussing. So the preprocessing of data, the classifier selection and configuration, and the actual prediction and evaluation. As you see, we just imported a number of data, a number of metrics which were previously computed, extracted, and then we defined a pipeline for machine learning, which in our case was composed of a preprocessing step and a classifier selection step. Afterwards, what we did is to get
the parameters, tune the parameters of the machine learner. And if we browse to the method, here you can see, let's take this particular example, that you see that based on the machine learner algorithm that we experimented with, in our case, random forest, support vector machine, and key nearest neighbor, based on the classifier, you have different parameters, and you want to tune the parameters. For instance, the max depth is, we experimented with different values ranging between 1 and 11. 1 and 11, and based on this range, the sklearn library is able to experiment with these different values and come up with the most suitable configuration for the random forest classifier in this case. Once got the parameters of the machine learning model, what we did is to implement the inner and the outer cross-fold validation, as we discussed. The inner validation was used to tune, to validate the model based on the parameters retrieved in the previous line of code, while the outer validation was used to actually see what were the capabilities of the machine learner on the test set. Here you see the usage of the algorithm exploited to identify the parameters, because in the previous method, what you have seen is the definition of the parameters that you want to tune. But of course, you need an algorithm that actually performs this tuning. And this algorithm is the grid search in our case, which is an algorithm that performs an exhaustive search over the parameters. And here you see that the grid search was applied on the inner cross-validation based on this metric, which we didn't see, but it's a relevant metric for evaluating machine learning models, which is the area under the ROC curve. Based on this value, the let's say the best configuration is identified. And finally, once you concluded the inner validation, you perform the outer validation, the cross validation, and measure the performance metrics for the machine learner. And finally, you print the metrics using the format that you like the most, and save the performance metrics. I'm running, time is running out now, but what I want to finally say about this source code is that if you see, machine learning is extremely complicated from a conceptual point of view. The problem of machine learning is to find a problem that deserves the use of machine learning, define what are the features for the problem of interest, what are the classifiers that must be tested, the dependent variable, and so on. So the pipeline is important from a conceptual point of view, but then the implementation can be fairly easy. Indeed, in less than 30 lines of code, we could have implemented the entire pipeline. And this is probably the most important thing to know about machine learning. So reason about the machine learning pipeline rather than use the machine learning pipeline blindly, let's say. That being said, I would like to thank again the watchers of this tutorial, as well as the MSR 2020 Regression Track co-chairs. I hope to have provided you with enough information on mining software repositories, machine learning, and the specific case of mutation testing. If you have any further questions, don't hesitate to contact me. Or I hope, let's say, that the material provided is enough to understand the topic a little bit more. Thank you everyone for listening. That's it. Thank you, everyone.